Okay, Year 12 PPE paper, 2018 January. We're going to go through each question for the multiple choice in this video. Let's start with question 9. So we've got a wave, and we have 2 points on that wave that are pi by 3 radians apart. So first off, let's draw our wave. There we go. You may be able to see from the moving marks that we had this on the year 13 paper as well. So here's our wave. We are told that we're looking at 2 points that are pi by 3 radians apart. Now we know the whole wave has got 2 pi radians between one point and then the next point, the whole wavelength along. One wavelength is equivalent to 2 pi radians. So if I've got pi by 3 radians, a third of pi, that's a sixth of 2 pi. So I'm looking at a sixth of the way along the wave. So here's my middle point, so I guess it's about there roughly. So looking at this point here and this point here, which is it is a sixth of the wavelength there. There we go. So we know that these 2 points are 0.050 meters apart. So we know lambda by 6, the wavelength divided by 6 is 0.050 meters. Which of course will tell us what the wavelength is, because if we know a sixth of the wavelength is 0.050, then we know straight away that the wavelength is going to be 6 lots of that. It's going to be 0.3 meters. 0.3 meters, so that's going to help us in a moment. We've got to figure out what the speed of the wave is. We know the frequency, and now we know the wavelength. So we know that there's an equation: speed is frequency times wavelength. So we're going to do 500 times 0.3. Yeah, that will give you your 150 meters per second. So the answer to question 9 has got to be C. Question 10. Uniform wire vibrating in its fundamental mode, and it's fixed at both ends. Now, let me just pause this for a moment. There is our wave, fundamental, so we've got a fixed point at both ends and it's vibrating in between those fixed points. We've got to figure out, we did the statement this is not correct, and I've helpfully put that in bold for you. So we're looking for the one that is wrong, so let's see. So it's talking about the statements that being correct or not correct for all the vibrating particles. Let's start with the first one. They vibrate in phase. They're all doing that. Every single one of them is moving up at the same time, stopping at the same time, moving down at the same time. So that's correct. We're not going to go for A. They vibrate with the same amplitude. Let's see. Well, this one here is clearly vibrating with a large amplitude. This one here is vibrating with a small amplitude. So they don't vibrate with the same amplitude. B has got to be false. So the answer is B, but just for completeness, they vibrate with the same frequency. Yes, they do. They're all sort of taking the same amount of time to do one complete cycle, so therefore they've all got the same frequency. They vibrate at right angles to the wire. Again, the wire is in this direction, the vibration is in this direction. So you know it is moving at 90 degrees at right angles. So the answer to 10 has to be B. Question 11. We've got a wave going at 20 meters per second, so our speed is 20, frequency is 100 hertz. So speed is 20 meters per second, frequency is 100 hertz, and we're going to figure out the phase difference between 2 points 25 mil apart. Now, your phase difference equation is going to require the wavelength, because if you remember, the idea is that you pick the distance between your 2 points, you divide by the wavelength, that gives you the fraction of wave between the two, and you multiply that by 2 pi, and that will give you your phase difference right there. So we need to know the wavelength. We know C and F, so because C equals F lambda, we know that lambda is going to be C over F. We just divided both sides by F there. So it's going to be 20 over 100. So we're looking at 0.2 meters. 0.2 meters in terms of the wavelength. Now we know that the points we're looking at is they're 25 millimeters apart. So we've got a bit of an issue here, obviously, because we've got millimeters and we've got meters. It doesn't really matter which way you go. I suppose technically it's always best to put it in SI units. It might be slightly easier to put it into millimeters here, and it wouldn't be a problem if you did, because if you had millimeters divided by millimeters, it would cancel out anyway. So as long as you keep the same unit for both, it won't be a problem. So just for the fun of it, let's do that. 25 millimeters excuse me, is going to be D. So we've got 25, and we're going to divide that by 0.2 meters, which is going to be 200 millimeters. And then you're going to times the whole thing by 2 pi. Now you'll notice, of course, that these are in terms of pi anyway, so really what you're looking for is 25 over 200 times 2. And if we do that on the calculator, excitingly, 25 over 200 times 2. Which means it's pi by 4 radians. Question 11, answer B. Not entirely sure what happened with the video there, but we shall persevere. Question 12, which one of the following types of wave can't be polarised? Well, we've got 3 electromagnetic waves and a sound wave here. The one that we can't polarise is the sound wave, because it's longitudinal, so ultrasonic is going to be the answer there, 12B. All of these are always transverse, so they can be polarised because they're part of the electromagnetic spectrum. Question 13. We're going to start messing around with different things here and seeing what happens to the fringes. One of these things will increase the spaces of the fringes, so the fringes will spread out over here. Let's think about what's going to happen. The width of the single slit is going to increase. Well, if we increase the single slit width, all that's going to happen is that we aren't going to spread the waves out. They're not going to diffract as much. So we might find that they don't illuminate both slit X and Y, but it won't have any effect on the pattern here, other than if you make this slit wide enough, then there won't be any diffraction. You won't get any interference pattern here. The distance between the 2 slits is increased. Actually, if you do that, what will happen is that the fringes will get closer together. Here's why. If you move X and Y further apart, then as you go down this screen, you don't have to go as far to get to the point where you are now an extra wavelength further away from one slit compared to the other. If, however, those slits are very close together, you're going to have to go quite a way down before you're so far down that you are a wavelength further away from the top slit compared to the bottom slit. If that's difficult for you to visualise, then ask me in person, or just accept it as fact, entirely up to you. But anyway, if you increase the distance XY, you're actually going to make the pattern come close together. Your fringe spacing will decrease, not increase. So it can't be A or B. A light of lower frequency is used. Well, let's think. If we have a lower frequency, then the wavelength is going to increase. And if the wavelength increases, then you're going to need to go further down here again before you get to the point where you're a whole wavelength further away from X than you are from Y, so it will space out the fringes. So the answer for 13 has got to be C. Just for completeness, the distance between the single and double slits is decreased. So we're just moving this again. All that we're doing is we're affecting how these slits are illuminated. We're not going to be affecting the fringe spacing. If we move this really close, then again the waves aren't going to be able to spread out. They're not going to illuminate X and Y at the same time, and you're just not going to get a pattern. 13 has to be C. Question 14, which of these stationary waves facts is an actual fact. Let's go to the video. Okay, here it is. So we've got our 4 statements. Let's check them with our actual wave. Can we put that there? Is that going to work? Sort of. Yeah, that's not too bad. Right, so first of all, particles between adjacent nodes all have the same amplitude. Let's check, shall we? Here are two nodes, and these two parts clearly don't have the same amplitude. This one here on my right is moving a lot further than the one on my left, even though they are between adjacent nodes. Here are your adjacent nodes. So A can't be true. Particles between adjacent nodes are out of phase with each other. Well, again, here are my adjacent nodes, and they're both moving down at the same time and up at the same time. So they're in phase. That can't be true. Just to remind you, if you've got particles between adjacent nodes, or if there's an even number of nodes in between the two particles, they will always be entirely in phase with each other in a stationary wave. If you've got an odd number of nodes between them, they'll be entirely out of phase. Part C, or option C, particles immediately on either side of a node are moving in opposite directions. Let's see. Yes, that is exactly what's happening there. As one moves up, the other moves down. So it's got to be 14C, but let's just check D anyway. There's minimum disturbance, the medium, and an antinode. Well, that's kind of the opposite of the point of what an antinode is, isn't it? The antinode is where you've got maximum disturbance. That's where you've got this disturbance here. The point where we've got minimum disturbance, of course, is the node. So it's got to be 14C for that one. Okay, question 15. Let's shift that. Copper metal is a good conductor of electricity because copper atoms in copper metal, blah. Okay, this really just comes down to you being confident with your explanation of conductors, insulators and semiconductors that we did at the beginning of the electricity chapter. If they've gained an extra or a free electron, then they're not going to be atoms anymore. They're going to be ions, they're going to be negative. That's not how copper works. They're ionized, so both ions and free electrons can move. It sounds like we've made a plasma there, and that's probably not true. Have a negative charge because of the free electrons. Again, copper isn't negatively charged, otherwise you get a static charge every time you touched a bit of copper. They've lost an electron to form positive ions and free electrons. That is exactly how it works. So these atoms, they don't hold on to their electrons rather so well. So some of the electrons will tend to drift off into the material. We'll end up with positive ions left behind, and then these free electrons are able to move around. So it's got to be 15D. Question 16. Okay, so we have a 12 volts battery, negligible internal resistance, we don't have to worry about any of that. Ideal diodes, so straight away looking at this I think, well, one of them is pointing one way, one's pointing the other. We can ignore one of these branches straight off, which is handy. Current always goes from positive to negative, and rather nicely for them, they have labelled that. So the current is going to go in this way. It can quite easily flow through this top branch. It cannot flow through this bottom branch because the diode is backwards, it's in its reverse bias direction. So we can ignore this entirely. The question is, what's the current through the battery? So in order to figure that out, all you need to know is the total resistance in the circuit and the total voltage supplied to the circuit. That will give you the total current in the circuit. So we've got 12 volts and we've got 60 ohms. You can do current is voltage over resistance, 12 over 60, which is going to give you 0.20 amps. Answer C for question 16. Question 17. Okay, now whenever we see a graph like this, we're thinking straight away of our EMF graph. Again, this is one from the year 13 paper, so you might be able to make out the graph we drew earlier in true blue Peter style. So it looks a bit like that. Current in amps, voltage in volts. Where it cuts here is the EMF, and the gradient of this graph of voltage against current for this kind of circuit is going to be minus R, because you're doing voltage divided by current. Voltage over current according to Ohm's law gives you some sort of resistance. In this case it's minus R. Where does that come from? Let me tell you. The definition of the EMF, or a definition of the EMF, is it's basically the supply voltage that you're giving to the circuit plus the lost volts. EMF is the supply voltage, and obviously we usually call that the terminal potential difference, and add on to that the lost volts lost inside the cell. So if we were going to draw a graph of V against I, we can figure out from this equation what we're going to get. So if I take IR off both sides, I'll end up with V is equal to epsilon minus IR, and then I can rearrange that to say that's equal to minus R times I. Let's just bar those i's to make it a little bit clearer, plus epsilon. That's your y equals mx plus c graph if v is on the y-axis and I is on the x-axis. So the intercept is going to be the EMF, and the gradient is going to be minus r. So hopefully, if you're familiar with your ideas of EMF and internal resistance, especially the graph, as soon as you see the V against I graph in the question, you're thinking straight away, there's your EMF, gradient is the internal resistance, or the negative of the internal resistance, and then you're in luck because the question literally just says what can you get from the gradient of the graph, and it is of course the internal resistance. So 17 has got to be A. Question 18. Now this is where it gets interesting. They give you a network of resistors. It's not a complicated network of resistors, but they have tried to make it look complicated by drawing it in an irritating way. So let's redraw this to make it a little bit more familiar to us. So we're getting the resistance between X and Y. That's the key thing, between X and Y. Here's your point X, here's your point Y. So let's consider where the current can go. Well, the first way is it can go straight through this 2 ohm resistor, straight from X to Y. So we know, so we're going to redraw our circuit. We've got X here, we've got Y here. It can go straight from X to Y through a 2 ohm resistor. They're all 2 ohm, I won't bother labelling the resistances. Or it can go another route, so it can go down here. First it goes through this 2 ohm resistor here, and then when it gets to this point here, it can split. It can go through this 2 ohm resistor, or it can go in a parallel branch through this 2 ohm resistor. So let's just draw that, and then through the magic of pens I can correct from my oversight and putting Y a little bit too far to the left, and there we are. So that circuit is that circuit. It's exactly the same. We've got X can go through this 2 ohm resistor, or it can go through a 2 ohm resistor and then splits into 2 parallel branches. So this through this one, and then can split through either of those and then recombines to Y. Now this probably is going to be easier to read than this because of the way that we've done it before. Now that you can see that, hopefully you can see how to work out the total resistance, the effective resistance in ohms. So if they're all 2, well, first of all, I can't add these together in one lump. I have to do it bit by bit. So this bit here is purely a parallel resistance circuit. No series in there at all. So let's figure out how much this is worth. As a general rule, you may well know that if you've got 2 resistors of equal resistance and you put them in parallel, the overall resistance will be half of one of them. So if this is a 2 ohm and this is a 2 ohm, the effective resistance of all of this is 1 ohm. But if you didn't happen to know that, you could quite easily work it out with the resistance equation. 1 over RT is 1 over R1 plus 1 over R2. So in this case it's going to be 1 over 2 plus 1 over 2, which of course is 1. So that means the total resistance of that one is going to be 1 over 1, which is 1 ohm. So 1 over RT was 1. I'm just going to emphasise that because I don't want to make it look like we've just added the reciprocals and then just left that, because that's a common mistake. What I've done is done 1, and then I've done 1 over 1, which is 1. Good, now we've cleared that up. So instead of having this one here, which is 2 ohm and a 2 ohm, we now know that's basically just a 1 ohm resistor, don't we? So that's 2 ohms, that's 2 ohms, worst handwriting. Okay, clearly my camera hates me. Let's press on. So I think we got to this being a 1 ohm resistor because it was a 2 ohm and a 2 ohm in parallel. So if we've got 2 ohm and a 1 ohm, that's basically 3 ohms here, and then I've got 2 ohm. So what I'm trying to do is add 2 ohms to 3 ohms in parallel. Again, we're going to use the same equation as before. You can see I wrote this the first time around when the camera clearly had died on me. So 1 over the total resistance is 1 over R1 plus 1 over R2, which is going to be a half plus a third. And then I did it algebraically. You can of course shove it in the calculator to figure out what that's going to be. But 1 over RT comes out as 5 over 6. So therefore RT is 6 over 5. We've flipped it, which is 1.2 ohms, which was option B. So question 18 you're looking at B. Question 19, let's see if we can get through a question without the camera fouling up. Resistance of a metallic conductor increasing with temperature, why? Well, quite simply, you've got to be a little bit careful with this, because, for example, there's bits that talk about how we can get into superconduction, or how we can sort of free up electrons, which is what you get with semiconductors. So specifically this is talking about what's happening with the resistance of the conductor, and it's a regular conductor because when you're heating up, its resistance is increasing. Now remember, this is the idea that if you heat up a metal, the particles start vibrating faster. If they're vibrating faster, it's harder for the electrons to get through, and therefore the resistance increases. So in this case we're looking at the amplitude of vibration of lattice ions increases. So the lattice ions, remember, are just the metal ions inside the metal itself. They're vibrating more. That's what we mean by the amplitude is increased. They're shaking around more, so it's harder for the electrons to get through. So 19 is going to be C. Question 20. Two resistors R1 and R2. Same material, so we don't have to worry about the resistivity changing at all. But we are told is the wire R1, it's got half the diameter and twice the length. And we've got to figure out what's going to happen to the resistance. Okay, now a key thing for this is to notice that if you halve the diameter, you're not going to halve the area. And that's crucial with this. If you had, for example, and it's not a square cross section, but if it was, if we had a square cross section of this whole area here, and then I halve the diameter, I'd be looking at this much. Okay, it's half the width, it's half the height, it's half the diameter. Essentially, well, obviously diameters don't apply to squares, but you get the idea. We're going to quarter the area, and it's the same with circles. If we come back to our equation, for the area of a circle is pi r squared. So if I then go to a second area where the radius or diameter, doesn't matter, either will be fine, is halved, because if you halve the diameter, the radius halves as well. My new area, AN for A new, is going to be pi times r over 2 squared, because now we've got half the radius of the square. But if we work out what that is, it's going to be pi times r squared over 2 squared, which of course is pi r squared over 4. So doubling or halving the radius rather is going to quarter the area. It's the same with diameter. If you halve the diameter, you're going to quarter the area. So with all of that borne in mind, we can figure out the answer to this question. We know that the resistance of our conductor is going to be the resistivity multiplied by the length divided by the area. Now we're told in the question that our new one has got half the diameter, so therefore it will have a quarter of the area, and the length is twice as long. So those are your two effects. We're going to make L twice as big, we're going to get a quarter of what it was before. If you multiply the denominator by 2 and only use a quarter of the, if you multiply the numerator by 2 and only use a quarter of the denominator, the overall effect of that is that you're going to be multiplying the whole thing by 8. So it's going to be 8 times as large. The answer to that one, therefore, for question 20 is going to be A. Question 21. The camera hasn't favoured us at the moment. That's very exciting. We've got a door hanging from 2 hinges 2.5 metres apart. This is a bit of a strangely worded one. They like to throw you a little bit. The moment of the couple that the hinges exert on the door. So here are hinges. They are basically applying a force to the door to stop the door from falling off. And the easiest way really to look at this is to look at, if you can work out the moment that the door exerts on the hinges, it will be equal and opposite to the moment that the hinges exert on the door. So let's think about what turning effect the door is having on the hinges. We've got 200 newtons and the line of action of the force is straight down the middle. It's a uniform door, so we know this is right in the centre here. So if I've got a line of action and the force straight down, the distance between the pivot and the line of action of the force is 1.5 meters divided by 2, which is going to be 0.75 meters. So we've got 200 newtons multiplied, that's our force, multiplied by our distance of 0.75 meters. That will give us our overall turning force. 200 times 0.75. And that's going to give you 150 newton meters. So if we've got 150 newton meters from the door, then we must have 150 newton meters from the hinges on the door. So the answer is going to be A, 150 newton meters. Question 22. Right, now this one, you could really get into the trig here and really prove that answer B is correct. It's a lot easier to disprove A, C and D. Often you'll find that often it's a lot easier to get rid of 3 options than it is to prove the answer to 1. So we're trying to figure out which of the bodies is in equilibrium. Like I say, if you come to this one, you can do the mental check straight away. You can say, oh, there's an upward force, but that's balanced by some sort of downward force here. We don't know how big it is. It might balance, it might not. We've got a force to the right, but there's a force to the left, a component from this 4.5 newtons, which is pushing us to the left. So again, those could cancel out. The real question becomes, how big are the components of this force to the left and downwards? Now you can work it out. So we know that the rectangle here is 2 centimeters by 1 centimeter, which means, let's pretend that never happened. That was absolutely terrible. Which means that we have a center here which is 1 centimeter across and 0.5 centimeters down. We know that the force is acting straight through the center there, straight through the center where those lines cross, the corner, as the correct term is. So you can figure out what's going on here, because we've got essentially now a right angled triangle. This side is going to be 0.5 centimeters. I'm running out of space. This side is going to be 1 centimeter, and so you can figure out how big that angle is with a little bit of trigonometry. You can then work out the components of this force horizontally and vertically and see whether they compare favourably to the 4 newtons and the 2 newtons. If 4.5 newtons with its components down in this direction gives you 4 newtons this way and 2 newtons this way, then it will beautifully counteract those other 2 forces, and we've got a situation of equilibrium. Now you could do all of that maths, but you don't have to, and you know, technically in the exam you probably shouldn't, because if you look at this you will find that it's a lot easier to disprove the other 3, as we said. Let's start with this one. This one can't be in equilibrium, because if I pick, for example, this centre here, I know that I've got a force on the right pulling me down and a force on the left pushing me up. So there's a rotational force there. Everything's trying to rotate me clockwise, nothing's trying to rotate me anti-clockwise. No sort of force can provide a moment to try and counteract that. So this can't be in equilibrium. It just can't. It's not satisfying the conditions for equilibrium. These 2, even more obvious perhaps. This one here has got a force to the right, and then a component of this is to the right. There is literally nothing to the left, and so we can't have equilibrium here. You could do it vertically as well. Total force of 2 newtons up here. We've got a component of this 4.5 newton force, which is always upward, also upwards, but there's no downwards force to counteract it. This cannot be in equilibrium. And this one, I mean, all the forces have got at least some upward force. There's literally no downward force there at all. So there's no way that this could be in equilibrium. So you can get rid of those straight away. You know it's got to be this one. And of course, if you run the numbers, you will find that the component of this force is 4 newtons in this direction and 2 newtons in this direction to counteract the other 2 forces. So question 22 has got to be B, 22B. 23, which I think is the last one. It is. Okay. Longish one, this one. So we've got a meter rule, there it is, and we've got a thread, so we've got a force acting in this direction here. So our tension force is acting there. We've got, does it say that it is uniform? It doesn't. It doesn't really matter though. We've got a force from the weight of this thing which is acting directly downwards, so we've got a weight force downwards, and we've got a tension force this way. Now all four of these diagrams, because you've got to figure out which one of these matches the situation, all four of them have got the weight downwards, and all four of them have got the tension force in the correct direction. So we can't eliminate any of those yet. There are a couple that we can just straight away, because we know it's an equilibrium, so all three forces have to cancel. That means, for example, that this one will not work. Because if I take, let's say if I take the three vectors in turn, so I go from here, I go do a T, and then a W, and then an R, which is basically there, isn't it? Then I haven't ended up where I am, or haven't ended up where I started. You're looking for three vectors that will take you back to where you were before. So that will not work, that's not in equilibrium. This one will. So that one might well be fine. This one, let's see, that's fine. This one, oh, that's not good at all. That's not going to give us equilibrium. So it's one of these two here. So clearly the directions of T and W are both the same for this one. Clearly T has a different size in these, but we can't really figure out how big that force is going to be, so that really won't help. It's the direction of R that's going to help us out here. We've basically got to figure out whether R is pulling in this direction or this direction. So do we have a force here? Let's bring this down. Is the reaction force that direction, or is it that direction? Now, I mean, if you think about it logically, you can probably figure out what direction the reaction force is. Imagine that you're holding it here. How is it going to feel? If it's being suspended by a thread, you're going to feel like you're having to support it. You're going to feel like you're having to put a force upwards, reaction force. So we're going to have an upward component of the reaction force. So it's going to be B instead of C. Both of them have got a leftward component, which is going to counteract this this rightward component of this one. Remember, the weight force is going to be directly down. But yeah, we've got to have a force upwards on this one. Let me just sketch it, just in case it's still not quite clear. There's our beam. We've got our tension force there. We've got our weight acting downwards. We have got to have our reaction force like that. There we go. Now you might think, well, why is it not the case that we could have a reaction force acting down? Because if you think about it vertically, let's get rid of that. Let's say if we had R like that, as it is in C. There you are. That also might be fine, because we could have the vertical component of R plus the vertical component of W adding up to the vertical component of T in the opposite direction. And yes, if you take the forces vertically, either could be true. But the reason this can't be in equilibrium is because this would give us a turning force, a moment about W, because this is trying to push me this way, this is trying to push me this way. We've got a turning force there. So we would have to, in terms of the moments, we'd have to have a force on this side which is trying to rotate me counterclockwise, clockwise for this one, to counteract the counterclockwise turning force of the tension. So all in all, you've got a reaction force like that, and therefore your answer has got to be B. And that is question 23 and the last of the video questions.